Ordinary linear regression is the standard mathematical tool for predictive modeling. At its core, it relies on calculating a simple weighted sum of input features. This page shows the math behind it. The core vector equation maps perfectly to continuous target variables, like predicting the dollar value of housing prices. But many modern machine learning problems deal with non-continuous, bounded reality, like predicting the binary pass-fail state of a student. Looking at the right side of this diagram, we see a mechanical failure. When we force a straight, infinite linear model onto strict binary data constraints, it immediately breaks through the hard ceiling of 1 and the hard floor of 0. Zooming in on the specific predictions, the model outputs values like -0.22 or 1.37. These impossible percentages are mathematically useless for actual science. Our models must physically respect the boundaries of the reality they are trying to predict. We face a dilemma. We want the computational speed and simplicity of a linear equation, but we need it to produce bounded results. The solution is the Generalized Linear Model, or GLM. This framework functions as a flexible, modular architecture for mapping data to predictions. This schematic illustrates the operational trick. Instead of modeling the raw output directly, the GLM models a transformed version of the expected output as a linear function of the input features. This architecture upgrades linear regression into a system capable of handling complex, non-Gaussian outcomes. To fix the breakdown, we shift our target. We stop trying to predict the exact random outcome of a specific data point and focus instead on the conditional mean. The center section of this diagram defines that metric. The conditional mean, represented by the Greek letter mu, is the expected value of the output given specific features. For binary data, mu represents the probability of the target class occurring. In this universal pipeline chart, the weighted sum of features is isolated as the systematic component, or the linear predictor, denoted by eta. Here we encounter a physical mismatch. The linear predictor calculates values stretching from negative to positive infinity, while our target mean is strictly confined. Because an infinite engine cannot directly drive a finite vehicle without breaking it, we must engineer a mathematical bridge between them. That bridge is the link function. Focusing on the center logit link, we see the inverse link function physically take the infinite score from the linear predictor and squash it through a funnel, compressing it into valid probability space. This page traces the specific algebra for logistic regression. We start with the linear log odds, exponentiate both sides, and algebraically rearrange the terms to solve for the conditional mean. The resulting inverse link is the sigmoid function. Because the exponential term sits in the denominator, the output is mathematically guaranteed to stay between 0 and 1, regardless of the input size. Routing the linear output through this inverse link physically saves the model from predicting impossible realities, ensuring scientific integrity. There is a widespread professional misconception that because it's called a generalized linear model, the final output changes linearly with the input. Looking at the left panel, we explicitly debunk this. A 1-unit change doesn't cause a flat, additive increase in probability. Instead, the center graph reveals the model is only linear in the predictor space before the inverse link transformation bends the output into the S-curve. Practically, this means changes in input have massive impacts on probability in the steep middle of the curve, but almost zero impact at the flat extreme ends. Confusing the linear predictor space with the probability space leads to severe business logic errors. Human behavior follows curves, not straight lines. Common machine learning algorithms are actually specific configurations plugged into the universal GLM architecture. Across the bottom of all 3 columns, we see the architectural constant. The linear predictor equation remains identical across every major model configuration. In the first column, we see the configuration for standard continuous data. We swap in an identity link and a Gaussian distribution to create ordinary linear regression. Moving to the center, the configuration for binary classification swaps in a logit link and a Bernoulli distribution. For count data, we configure the system with a log link and a Poisson distribution, creating Poisson regression. Once you master the underlying pipeline, you no longer need to memorize individual algorithms. You simply engineer configurations based on the physical shape of your data. Furthermore, the GLM framework translates the classical language of statistics into the modern language of neural networks. The assumed probability distribution of the random component physically dictates the loss function used to train the machine learning model. This three-step flow proves the equivalence. When you take the statistical concept of Bernoulli likelihood, apply logarithms, and multiply by -1, you directly derive the binary cross-entropy loss used in deep learning. Looking at the bottom row of this summary slide, we see why this architecture remains so dominant. It is inherently interpretable, statistically principled, and highly efficient. Generalized linear models provide the foundational mathematical layer that scales up to form the basis of modern predictive architecture.